Professor Antonino Filippone is an expert in computational aerodynamics and works in areas such as rotating systems, rotorcraft, advanced propellers. He is interested in aerodynamics, acoustics, propulsive emissions and aeromechanics. He is a fellow of the Society and also of the Institute of Mechanical Engineering. Professor Filippone.
Thank you. Thank you, Mr. Chairman. Thank you, everybody, for inviting me here today. And this is obviously an unusual theme, the contra-rotating props. You haven't seen many of those. You probably won't see them ever. And you may ask yourself, why would anyone want to have contra-rotating props? Anybody has an idea? Torque. Yeah, torque. Yeah, that's an idea. In the 1930s, it was about speed. So the only way to achieve a high speed was to use contra-rotating props. Because very smart engineers, they thought they couldn't have two different props. So they had to have one on the same axis. In the 1940s, it was about increasing roll stability. So you had a very short takeoff. And to avoid roll instability at high torques, as we said before, the idea was, let's put a contra-rotating propeller so you can neutralize the torque from, in one direction, or you can put the torque in the other direction. And the war was important to have the sort of airplanes. In fact, many of them were designed during the war years, and just after the war years. In the 1950s, it was about increasing range, because someone was able to demonstrate that contra-rotating props were more efficient than ordinary props. In the 1960s, nobody cared. And I'll tell you why in a moment. Then everybody went to sleep until the 1980s. In the 1980s, they found out there was a fuel crisis. And they borrowed the idea from the 1950s, these props are more efficient. So I wanted to look at them again. So more efficient. It was about efficiency, reduce fuel consumption. In the 1990s, it was about reducing noise. And since then, we haven't moved very far. It was all about noise. All the work you can find from the 1990s to today is about noise. In the 2020s, we're told by people who got a lot of money from the taxman that we're not there yet. So we are almost 100 years down the line, we're not there yet. That's worrying. So let me look about the Pioneer. This is the Pioneer here, 1933, an Italian airplane. Fastest seaplane, world speed record. From the Federal Aviation, it was of course certified, and now it's been superseded because those airplanes don't fly anymore. Beautiful airplane. It's just look at these pictures, these vintage pictures. To my amazement, I mean, this airplane exists in some museums. You can go and see a replica of this airplanes, but the engine, to my amazement, the engine still exists. And I found out that just in the last year, in the autumn, that the engine exists in a museum in northern Italy, and they were celebrating the 90 years of the engine to just basically they were trying to run again the engine without props. That was an IC engine. That was a revolutionary for the time, because there was a coupled engine. I'm going to talk about coupled engines in a moment. So one engine moving one prop and the other engine moving the other prop to the opposite direction. So it was a fast moving engine. So 1930s, and then that's it. So this is summary of what existed and what we find today. About 70 airplanes, they've been successful, moderately successful as a contra-rotating props. About 15 types reached the operational service. You can read that yourself. There will be tests, and down to one passenger service. The Tupolev, that was a Russian, Soviet Union, 114, Russia, operated between 1964 and 1968. In fact, it was taken out of service just a couple of years before the first noise regulations came into force. Nobody cared about noise in those days. There's some interesting pictures on the internet. There is no measure of noise. No one ever went out with a microphone to test how much noise it was making, but to all accounts it was a very, very noisy airplane. But it's gone. Manufactured in Manchester. I like to say this because I come from that part of the country. So the Avro Shackleton, which I believe is going to be moved here to Gosford, is it right?
No, it's staying at Avro Heritage.
He's staying there, right? So the Ferry Garnet, which is over here, the Ferry Garnet to the right, the Rolls-Royce Merlin engine, and the Aerodynamic propellers, which I found out to my amazement, that the factory was just 5 miles away from where I live, except that there is nothing, absolutely nothing that says there was a factory at the point. The only clue is that the road leading to the point is called the Havilland Way. I always asked myself why the Havilland Way is because in the 1960s, up to the 1960s, it was the propeller factory of the Havilland company. And of course, that's gone, like many other things. And this is the Ferry Garnet, early airborne warning. They produced about 350 of this, believe it or not. Those of you who are old enough, you might have seen one flying. And that was characteristic because he had the Z type of a wing, so he could be folded twice. So it could be stored on an aircraft carrier, but it was famous for ourselves. I mean, it's important they had the contra-rotating props. Look at modern props. There is a variety of modern props here. So what you see here is a very, very large props. You know, some of them have in 6 meter diameter, one on top. Is a Russian or ex-Soviet Union Aerosila, I'm going to talk about in a moment, Aerosila AP60, so 6.2 meters diameter. Massive, massive thing, above the ceiling here, I believe. So there was a contra-rotating prop. The one to the left is Hamilton prop 4.5 meters. Is again a contra prop, a 3x3. And the one to the right is a prop which operates to this day. So SB27 powers the Antonov, I think it's Antonov 70. So very high solidity there. And if you go to the bottom line, so there are some very large props, which are single rotation props. The one here, FH386, is the prop of the Airbus A400. The one in the middle is the new generation prop for the Hercules. There is Hercules part of there. So the Hercules is a props with 4 blades. This is an earlier version of the aircraft. Newer versions have 6 blades, and the new one is this Hamilton Sunstrom 2000. There are 8 blades. Something revolutionary for the 1940s, because in the 1940s they believed they couldn't fit more than 4 blades on a single hub. The one is a front open rotor. They spent about £100 million, I think, in research, and they were told that we're not still there. They look like, the blades look like flags, and there is an uneven number between say, a different number of blades between fore rotor and after rotor. In the old days, you had the props that had the same diameter. The front rotor and the after rotor had the same diameter and the same number of blades. Same solidity. It's not like this anymore. Now, why is this timely? I'll tell you how I started this, because I wanted to write something interesting. I was finishing a second edition of a book, and I thought, you know, it was getting a bit boring, too much math. I want to have something interesting, but because one of my students did the good thesis, I went to look at this review of what was the review of the subject. And I thought, wow, this is rubbish. Not against my student, they did a good job, but I thought the review was nowhere close to what I wanted. And then when I started looking at the contra-rotating props, I opened a can of worms. Nobody had done that. And I discovered this, that, first of all, I wanted to look at what are the successful ideas, why people have been working for so long without actually reaching a solution, and the errors of judgment are very difficult to actually accept. This is valid in engineering, like any walk of life, and believe it or not, there have been in the past very senior engineers who made really serious mistakes. But we'll never accept that. I'm going to show you why. So, the contra-rotating propeller, you think is the future of aviation? It will always be the future of aviation. So the myth is that The contra-rotating propeller offers propulsive efficiency gains compared to the conventional propeller, so that's the idea there. The reality is that there are much more difficulties, so we have to pay the price somehow with the vibrations, with the flutter, weight, noise, pitch control, additional maintenance cost, and everything else that goes with it. All this for a few percent at best in propulsive gains. Now I'll show you why. So a typical curve of propulsive efficiency is here. So basically you have the conventional propeller which reaches a maximum of about 78 to 82% cruise. And the contra-rotating propeller, they claim up to 86% on a good day. Okay? It's not just the propulsive efficiency, it's the fact that you can fly faster. So look at the advanced ratio, you can fly faster at a high efficiency. So that was the idea. It was the idea of the Russian designs, which I'm going to discuss in a moment. I said before the Russia and so on. So you could fly actually faster, not only efficiency. So more efficiency at a high speed was good, but the fact is that the decrease in efficiency by 6 to 8% is misleading, because that doesn't account the overall chain of efficiencies. Means the engine, the increased weight, the increased complexity is not just the efficiency of the prop. Is efficiency. Efficiency is always a chain. And therefore, if you were to buy one of these ideas, be careful, because they always try to sell you something. So you need to consider the overall efficiency, including the engines, which is the thermodynamic efficiency of the engine, the increase in weight, the complexity, and everything else. So the 6 to 8% is actually misleading. The other thing we've been told is about the swirl recovery. So how do you do this? So you have one prop rotating in one direction, you have the other prop rotating in the opposite direction, and the idea is that you take advantage of the fact that the slipstream is rotating in one way, so you catch these combs and you rotate it the other way, and therefore there is less of a momentum loss, angular momentum loss as the slipstream is adjusted in the axial direction. But this is not true. This is only true for heavily loaded rotors. It's not true for lightly loaded rotors. Unfortunately, the people who did this analysis about 40, 50, 60 years ago, they didn't know anything. They didn't know anything about computational aerodynamics. So they couldn't actually see that the efficiency gain was a chimera. They could only achieve that efficiency gain at a very high speed and in particular circumstances. The other thing is, you have a large torque. If you have a large torque delivered by a humongous engine, what are you going to do? You need to absorb the torque, so you have a big propeller. So you increase the diameter, but up to a point you can't increase the diameter more than that is possible, say, because of ground clearance. So you increase the number of blades. But this couldn't be done. It wasn't very easy to increase the number of blades and move to more than 4, sometimes even 5. So increase the blade count was the first idea, or increase the blade activity factor. The blade activity factor is a measure of the size of the blade, effectively. The bigger the blade, the more torque it can absorb. So they could do this up to a point. And finally, if they cannot do it, they cannot get the solution by a number of blades and activity factor, you would have one other propeller at the back. So use of contra-rotating props. So there was not just a question of efficiency. So in the early days, 4 blades were the practical limit. So they would tell you, no, we can't fit more than 4 blades on a single hub. So the only way to do that was to increase the number of rows. So you have 2 rows, so the front propeller and the aft propeller. Eventually, when engineers became smarter, they could fit 5 blades and then 6 blades, and now you've seen from the previous picture, they could also fit 8 blades. In fact, the modern what's called prop fans, they can fit 13 blades on the same hub. So this is how the world has changed. So I need to be specific of what this contra-rotating propellers means. So you have a contra-rotating propellers when your 2 props are coaxials and they're driven by a single engine. So there is a transmission system that is needed there. There's a gearbox, I'm going to show you in a moment. But there is a single engine and there are 2 shafts, they are coaxial, they drive 2 contra-rotating propellers. Then you have the coaxial contra-rotating propeller, so 2 props or coaxial shafts, each driven by a separate engine. That was the example of the Mach-E 72 I was showing before. So there was an IC engine we had, because at that time they only had IC engines. So one engine would drive with one prop in one direction, the other engine would drive the prop in the opposite direction. The counter-rotating props are of different shafts. Okay, so if I take, for example, the C130, you think that you could have, two props rotating in one direction, so in one direction, the other two props rotating in the opposite direction. You could do that, but it costs more money because you need to have left-handed props and right-handed props. But that's something that was done. So on different shafts, for example, the Lockheed 130, then they changed, and they used a system called synchrophasing in order to reduce noise, and they started rotating the props in the same direction. The new propellers in tandem, where the props are aligned along the axis, but the distance between them is very large. So there is one prop, and then one diameter distance downstream, and there is another prop. So the interference is very small. In the 1970s, Hamilton Standard came up with a new idea called the prop fan, so very highly loaded props, which are unducted. I'm going to talk about that in a moment. And then other names like tandem propellers, dual props, open props. And in fact, in this country, the props were not called the propellers before the war, they were called the air screws. But then the Americans started to dominate, and the word air screw disappeared. Nobody talks about air screws anymore. Propellers, because that's the American definition of the air screw. So we've got the propellers mounted forward, mounted aft. I'm going to show it this way. So examples are like this. So you see on the left you have a coaxial contra-rotating props. You have the direction of flight. The engine is behind the props. Okay, so this is a tractor. In the many modern embodiments, the props are behind the engine, so they are pushers. On version C, you have a contra-vanes. In this version here, the prop is, say, a conventional prop, and the vanes are fixed. So instead of recovering the swivel of the wake by having contra-rotating props, you use fixed vanes. Now, this is an idea that goes back to the 1920s. It was proved as being also a fallacy, and just 10 years ago there was a big project funded on the use of vanes, because people don't read the literature which is 100 years old. What did they find? What we found, well, I wasn't told enough at that time, but they said, this is a good idea. In fact, there's a tandem I was mentioning before. There is a prop on one side, there is the other prop mounted on a separate engine. The distance between the two props is about the diameter, sometimes even more. So the contra-vanes are revisited in recent years, but the reality is that they make they give you no advantage. Okay, so these days now we have difference in diameters, difference in number of blades, difference in pitch, and difference in torque split. So in the old days you would think you had half the torque from one prop and half the torque from the other prop. Now there is advanced research will tell you that the torque split is not 50-50, is something else. This is also an interesting engine. So first of all, I want to say about coupled engines. I showed you a coupled engine at the start. So you have two engines moving each of them a propeller. So this is the definition of coupled engines. Anyways, we have two engines, in this case even three engines, are joined together to provide more torque. So they joined to drive one propeller or two coaxial propellers. There was this American design. This was essentially using three coupled Allison turboprops. The original turboprop was called the T44, and the combined assembly was called the XT44. That was not a very reliable engine. It was prone to failure, and Allison, which was one of the pioneers in the turboprop industry, in the end couldn't make a turboprop to work, and they almost left the industry. They came back into the industry. In fact, for many years they specialized in transmission systems. You see here, there's the transmission here. There are three shafts. There's a big gearbox in the middle. They specialize in transmissions. Many American cars mount Allison transmission systems. But the packet turboprops, now the company is owned by Rolls-Royce. And it's the only company owned by Rolls-Royce that makes turboprops. In this country, we basically sold all the rights to foreigners. We don't make any turboprops anymore. So what is power loading? So if you take the year of first flight and you basically take the power of these props, you divide it by the disk area, you see how these props get more powerful, with the years. It's almost linear in there. And you have ice engines in the early years, so there are the round dots. And moving to the years 1960s, then, as I said, everybody moved on to something else. You see that the power loading of these props is increased. Now, if you look at the top right of the page, there is a single rotation propeller. It's very highly loaded, and that's the propeller of the A400M, extremely powerful. So even the one then to the right there is the NP 2000, is single rotation propeller. So there is no difference anymore in the power loading between the old contra-rotating props and the modern single rotating props, and that's one reason why I don't think we need to go back to that technology. This analysis are done based on the fact that I consider equal torque among the blade rows, equal propeller diameter, equal design power. It's not necessarily the way, but I mean the chart works fine. So what makes a propeller in the contra-rotating propeller? They are very complex mechanical systems. One of the great complexities is the gearbox and the change in pitch. Changing the pitch is not easy. You're not going to go down there and change the pitch. You need systems which can be hydraulic, can be electromechanic, and they're all complicated. So you have hundreds of parts. Now you have dozens of systems, including the icing. These days we've got the icing, we've got the hub, we've got the shaft, we've got the pitch control system, electrical parts, so they are hydraulics and so on. Auxiliary power units are always used. Propeller control units, like governors and electronic controls. The propeller electronic control is a very important part of a propeller these days, called the propeller electronic control. Software and FRAeS. Believe it or not, there is a FRAeS also in the propeller. Propellers have to be certified to the highest standard, like aircraft. So the propellers are certified, like engines are certified, like aircraft are certified. So how do you certify that? So there is, of course, a process to certify propellers. There are rules for the EASA, the Federal Aviation, and now also the Civil Aviation in the UK, since we got Brexit done. But no CRP is currently certified. There is no one in the Western world that can fly a contra-rotating propeller. There are no rules. In fact, the Code of Federal Regulation, FAR, Part 35, Section 216, say the complexity of contra-rotating propeller is not been considered, and therefore additional requirements may need to be established. So if you design the new contra-rotating propeller, there is nothing that will allow you to certify that propeller in the Western world. Nobody knows, despite having that experience of 90 years, thereabouts, and about 70 sort of successful or medium success propellers around the world. So the ESA term of reference say that the CRP should be certified under engine regulations. So now they come up with the engine regulations with the provisions for characteristics for rotor-rotors, including bird ingestion and blade out events. So what are we doing about that? Who knows? So engine layout. And so this is what we have, is 4 main architectures that I found in the most of the successful aircraft. So starting from the top right and left, we got the oldest example. So we got 2 engines, then will be essentially 2 clutches, of course, and then will be a central shaft with an idler gearbox, and there will be a Coaxial shaft. So there is an outer shaft, and there is an inner shaft, each of them rotating in the opposite direction. So there is a twin engine called the contra-rotating prop. On to the right, we have a twin engine Coaxial prop. So we've got 2 engines. In there, we've got 2 clutches, and then you have 2 gearboxes. So you have an outer shaft and inner shaft. And this was typical of 2 aircraft, which I'm going to discuss shortly. One was the Douglas XP-32 American, and the Fairey Garnet, which was British. The third one was really bizarre. I mean, there are some pictures, if you dig deep in the internet. This was really bizarre. There were 2 engines which were not parallel to a shaft, They were at an angle. I don't know who came up with the idea, so engine 1 and engine 2, so it got to this complicated gearing there. So gearing is G1 and G2, so you have two coaxial shafts, outer and inner. So this was the Bristol Brabazon Type 167, which, as you know, never went anywhere. Yeah, never flew. And then it was the Sanders Row. Again, another monster, another dinosaur that never flew anywhere, despite the propaganda around the aircraft. You got an engine 1 and 2, and then complicated gearing, in order to have basically a V-drive parallel twin engine coaxial props. I would say the two at the bottom, the Saunders Row and the Brabazon, they were designed around the same time, late 1940s, early 1950s, which were really a critical time, as I'll show in a moment. So the Saunders Row was one of the biggest mistakes probably in British aviation, and in fact the government cut the project short, and they basically destroyed the only goal that was supposed to finished. I think it flew only 30 hours before they realized it just wasn't going anywhere. So you find the original drawings. The original drawings were not done with the SolidWorks, with the CATIA, AutoCAD, nothing like this. You needed to have artists to actually draw a propeller and the propeller, in the bearings. And these are some examples of some propeller systems. So 1 degree of freedom, I should say, how many degrees of freedom you have. You can have 1 or 2. In 1 degree of freedom, the pitch is controlled automatically on both propellers. So there was really not very much you could do. As you increase the pitch by 1 degree on one prop, then you increase the pitch also on the other prop, the same amount. So that was hardly very efficient, despite what was claimed. What you need is 2 independent pitch controls. So 1 degree of freedom was 2 props slapped to each other, and there was that beautiful design called the Saunders Row, the Princess. It was called the Princess, I have to say. Yeah? It was called the Princess SR45. And in fact, that project killed the company. The company was going kaput after the project. And the 2 degrees of freedom, when each row had independent pitch control, was totally independent. So there was a Bristol Type 168, so it had a better torque split. So look at this design. So there are different colors, one for the fore prop, another one for the aft prop. So there are, this is a Rotol prop. Rotol these days is called Doughty. And then it's part of the DG Contra-Rotating G just down the road. So Rotol independent control, contra-rotating props. Amazing designs. It's interesting to talk about the engine research in the 1940s, British engine research. That was actually very interesting. The industry was buoyant then. So they had a couple of engines, as I was mentioning at the start. So there were piston, there were diesel, and there were turbo compound. So I'll show what the turbo compound is. The ferry company, which is no longer in business, had this engine here, the Morak P24, just before the war. Never entered production is this monster here. You got two engines in there, 2 IC engines, and you got 2 basically contra-rotating props. These are FARI contra-rotating props. They were built under license from the Americans, Reed propellers. And this monster never entered the service. So they had 2 parts of the piston engines delivering 750 kilowatt each, driving 1 pump. It was the same as the Macchi MC72. And you find out what type of prop you have there, because you can zoom these days, and there is always a logo on the prop, so you can find out who's the manufacturer of the prop. So they were very own props for the license. So flight testing not with a ferry battle, and again it wasn't successful, so they killed the project. In 1947, 1950s, there was this other company called Napier. Napier had the 2 engines. Napier 1, Nomad 1 was a turbo compound engine. It was a diesel plus gas turbine. Interesting design. I think I got a picture, and they couldn't sell it. Nobody wanted to buy it. It was too complicated. So they designed a Nomad 2, where Nomad 2 was delivering the power for a single propeller. So they went from contra-rotating propellers to single rotating propellers from one version to the other. And the NIAD just later is this one. This was good. This was called a truly contra-rotating engine. You have, I couldn't find out which contra-rotating prop was that. It was designed for Blackburn P54. The program was cancelled, and the engine never flew at all. So the gearbox is aligned with the turbines easily there. So this is a drawing I found, but there has not been tested as far as I know on a real aircraft. So turboprop, twin turboprop, and 2 banks of three-bladed props in there. This is also another masterpiece of engineering, the double Mamba. The double Mamba was designed by Armstrong Italy, and actually this was successful because this operated for over 30 years. So the original engine was called the Mamba, and then they had to couple 2 Mamba, one side by side, and then this complex gearboxing, and the shaft that coming out there, actually there is 2 coaxial shafts in there, powered the fire gunnet, which I was showing before, until about 1980. And finally, I would say before there is the Python engine powering the Avon Shackleton, and the Western Wyvern, another interesting aircraft. The Western Wyvern was the last fixed-wing aircraft that the Western company had before they moved into rotorcraft, into helicopters. This was in the 1950s. So this was a turboprop engine. So the British engineering research continued with the Bristol company. Bristol had the Proteus in the 1940s, 1950s. The 2 versions of the 600, there was coupled engines that failed. They never flew anywhere. So coupled engines, this is what I was showing before. The Bristol Brabazon, you have a V drive in there, which was too complicated. The 700, the single engines, was successful. It powered the Britannia. The Britannia didn't fly. So it was a single rotation prop based on the same type of engine. Okay, and this was the Nomad 1, the final version. This is the turbo compound. Now I have to say something here, and hopefully that will make it interesting. One late night I was looking at this engine here. I did it just on a big screen on my computer. It was late, as I usually do, and then my wife comes into my office, slams the door open, and she says, "Why are you looking at that crap engine?" She didn't know anything about this. But she said, "Why are you looking at the crap engine?" It's my French. And I kept looking at it. And in fact, I thought, this was fascinating how complicated was the engine, but the reality is it never sold. It was good because you could use a diesel fuel as long as jet fuel. So in times of need, you use less valuable fuel, which is diesel. But it was just a mistake. I mean, it was a masterpiece of engineering, but it was just too complicated. So one prop was turbine-driven. So the other prop was turbine-driven. The inner prop was diesel engine-driven. The intake is here at the bottom left. There is the internal combustion manifold, the 12 cylinders, 2 strokes. The exhaust is there at the right with the turbine. So this was the Nomad 1, 3x3 contra-rotating propellers. It never sold. Remember the story I said before. So the companies had to go to single rotating props they could sell. So they tried that. I was amazed by this picture here. They did fly it. So they did fly it, a test flight on the Avro Lincoln. I found this picture from the IME archive. The amazing thing is that they modified the nose of the airframe. So they fitted this monster engine at the center of the nose. And the 4 props, 2 by side, they remained installed. But in flight, they were put into idle mode. They were feathered. So the aircraft is flying with the central contra-rotating prop, but the propellers on the side are stopped. You could do these things in the 1950s. Today they will arrest you on the spot, unless you have the certification, at least the civil aviation temporary license for flight tester. There is no way you can do that. Well, they found out things, and it will be interesting to look at the original reports and to see what they found out. But it's amazing, like the 4 props are actually idle in there. So I want to say a few trivia about the engine names. You know, because these days engine names have no meaning, they're just numbers. But in the old days, particularly in Britain, these days in France with the turboprops, engines have a proper name. So you see that the ferry produced only 2 engines. They're named after royals. So there was a monarch and there was a prince. Armstrong's Italy had the piston engines named after big cats, for example, cougar. And the gas turbine engines were named after reptiles. So there was a mamba, and the couple mamba was a double mamba. Sounded very good, double mamba. The Bristol aero engines were named after Greek mythology, so remember the Proteus. One was successful, one was not successful. Rolls-Royce, birds of prey for the icy engines, and the British Rivers for the gas turbines. And again, I couldn't find out exactly how they named their engines. I looked at all of them. They mixed the blended weapons with some other animals, and a couple of engines were called the Naiad and the Nomad for whatever reasons. I don't know, someone can find out for me. But I found that fascinating. Okay, so really impressive efforts in those days. You could do anything. In fact, maybe I'm old enough, there was an aeronautical research council in those days. So powerful was aeronautics. So with the Rotol, with the Avalon, which are gone, the ferry, which are gone, the Terra, which is also gone, the Ministry of Supply, which is also gone, and of course the Aeronautical Research Council, which is gone. They're all gone, unfortunately. So things came to a head in the 1950s when the chief engineer, Gardner, Mr. Gardner and Mr. Bratt of the Avalon said, on payload, the range passes, you can read that yourself, it's just not worth looking at this CRP. These were the chief engineers of 2 very important companies in the 1950s. If only the military pay money, then we'll look at that, but on the commercial side, it's just not worth it. It's the complexity that is killing me. And Favors, another chief engineer at Rotol, just down the road, so they found favor in civil aircraft, and we are late 40s, early 50s. Large on account of its greater expense, complication, more complex service, maintenance problems. And guess what? People are still trying with them, just they don't read the papers from those days. They don't talk to the people who knew, the people who paid with their own skin for making those mistakes. Yeah, that's what happens. So this was 1956, the previous one was 1954. There were beautiful reports, really beautiful reports from those days. The Hurricane fitted with Rotol, 35-degree pitch range, air screws, that's called air screws. So this is, doesn't say the year, but they're called air screws. And the other one, they're called the propellers, so they must be older. So May 1944 says that Rotol 35 required a total load of 3 tons to move the blades. You can't just go, you stick your hand out and let's move the blades by 1 degree pitch. You need an enormous force, particularly at a very high load. So 3 tons in this particular case. But let's talk about another success story. Is the Westland Wyvern, beautiful airplane. Look at those massive propellers. That was shown at the air show at Farnborough in 1950. So this is model TF1, the first one powered by Rolls-Royce Eagle piston engines. And they moved on with that. They did the TF2, TF3, TF4, and TF4 was actually powered by turboprop, so the Python I was mentioning before. And this was the prop, 4-meter diameter, 13 feet. Those who like to talk about feet, was 4 feet. That was amazing. Look at the beauty of the propeller. About 130 of those were built. And then the Fairey Garnet, I mentioned it before. So there was a career-born reconnaissance for the Air Force, was in service for 30 years, and after he was taken out of service, at least one of them became a research test bed. I think they gave one away to Hamilton Standard and NASA. NASA did some tests, also noise tests. And I know that one of them was flown at an air show in North America, which is the Oshkosh Experimental Air Show. They run every year. I don't know if anybody knows about the air show. I've been there once, interesting place. And it was flown for about 10 years there at Oshkosh. So they built about 370 in all versions. So this was actually a very, very successful aircraft. The engine was the double mamba I was mentioning before. And the blade geometry data are not known, but they've been digitized. So those of you who do a bit of aerodynamics, you will find we find that it's actually quite nice to have the blade sections of this aircraft here. So they're similar to NASA 16 series. I cannot talk about that, otherwise it takes us too far. But NASA 16-digit airfoils were designed in the 1950s to respond to the need to operate at transonic Mach numbers. So the fore and after blade rows have the same diameter, but they have a different thickness, and each blade could operate independently. So you could run the aircraft with a single rotating propeller, the other one feathered, for example, in taxi operations. So we have some acoustic data which have been published, and these are good for those people who work on acoustics and acoustic simulations. So this is the only aircraft I know. Probably there is another one for which acoustic data are actually known. So these are politically driven projects. So I say the Brabazon was politically driven, I think, and the Princess was also politically driven. And also, you were curious about that, you can type the SR-45 Princess. You find some amazing things, not all very good about this aircraft. Okay. So 1952, massive flying boat to serve the Empire. Was designed to serve the Empire, to fly to India, to fly even to North America, to New York. 10 turboprops. There were 8 of them arranged in couples, and the engineers were so smart. They actually had the 2 different variants of the engine. Okay, some of them were operating on a single propeller, and other ones operating on counter-rotating propellers. So the 2 props which are inboard are counter-rotating propeller, and the propeller outboard is single rotating propeller. So they mixed engines and they mixed single rotating and counter-rotating propellers. I don't know what they had in mind. So you got 3 shafts on the left, 3 shafts on the right. So V-drive Proteus 610 engine, and they were marking this, like quarters with comfort and privacy of an ocean liner's cabin. So yes, I said before, 30 hours of testing, actually it was 45 hours of flight testing after the government actually axed the program and the whole was scrapped, probably out of shame. And there was the drawing of the inside of the propeller, so the mechanism are just amazing. There was aerospace engineers in those days. So remember, 1952. Now look at the timeline of the projects. So we have 1950. 1950, you got the Bristol Brabazon. Just afterward, 1952, the Princess. And just then, the Comet came to service. But the Comet was a jet-powered airplane. So why would anyone spend money in developing 2 competing contra-rotating props when there was no real future? The future was the jet engine. And that's where the British research on contra-rotating props just stopped.
Yeah.
Because then you have the Avro Vulcan. The Avro Vulcan came just 5-6 years later. You got the Avro Vulcan here in the house. The HP-80 Victor. So, no future for that type of research. Let's go to America. America, again, they've been pioneers. They've been very daring. They had the money to spend more than we did. And they didn't have any certification requirements. So interesting, this one, Jack Northrop was a fan of flying wings. And one of his designs in the 1930s was this flying wing XP-35 with after-mounted counter-rotating propellers, which had a 7-meter shaft. Now, if you think about 7-meter shaft, you can think of all the vibrations, the flutter problems that are there. But they did build something with a 7-meter shaft. So there, the propellers you see there are mounted at the back of the wing. It was very difficult to mount the prop on the front because there was a very highly swept wing. There was less sweep on the trailing edge, so they could mount the prop at the back. Here, another interesting design, the Douglas X B-42, after-mounted counter-rotating CRP with a 9-meter shaft. Unbelievable, 9-meter shaft. With the Allison turboprop. So this is a public domain photograph, and this looks like a toy. They flew one, I think it crashed, and they flew another one, and I think he's in a museum. So this is the way it looked like. Again, a beautiful piece of engineering, but I will not allow anyone, if I was a chief engineer, to do something like this. Look at the length of the shaft. Of course, there are some joints in there to allow for a bit of movement and reduce vibrations, and the big gearbox there at the end. The shaft is a contra-rotating shaft at the far end at the right. So this is the twin engines, so the two T40 Allison turboprop. So flight problem encountered, but there is hardly any documentation. 1950s, vertical takeoff and landing. There were two projects. The Americans had the money, so they decided to split the money between two competitors. One was Lockheed, and the other one, I can't remember, Convair. So this is Convair Pogo. And Lockheed Salmon and Convair Pogo. They were called tail sitters. So you can imagine this airplane here is sitting on the ground, and then with the power of a contra-rotating props, is taken off vertically, converting to horizontal flight, and then converting back, basically sitting again on the back. And this particular airplane did 6 successful flights. I don't know what they had in mind. I mean, they proved that it flies, but I mean, at that time, in 1950s, we already had helicopters. So they were completely out of step. Oh. This other one, this is Hitler X-18. They failed but never abandoned. So basically they realized that the conveyor had failed, but decided to cannibalize the engine. So they cannibalized the conveyor engine, is over there. And they cannibalized an airframe. This is a Chase YC-122. And they put a thing on the stand and see if they can convert. So they got a tilt wing. And that was probably the only tilt wing we had until maybe a couple of years ago. Now we have people going back to tilt wing, but this is for UAVs. So there are subscale aircraft that don't carry people. But we imagine that you are in a critical situation where you're tilting like that, you know, it's difficult to convert to level flight. So the propellers were from the Convair Pogo, and you had Allison turboprops, which were not very reliable. So this was America. I go now to the Soviet Union. The Soviet Union, interesting, they are the ones that spent more money on contra-rotating props. The only advanced country that never spent any money on contra-rotating props was?
France?
Germany. Huh. There is not a single example of contra-rotating props coming from Germany. There was nothing before the war and nothing after the war, and I would say the reason, because after the war they were just they were kaput. They were not allowed to do aerodynamic research. There could be a reason, but the main manufacturer of German propellers, a company called the VDM, essentially didn't exist after the end of the war. So built around the powerful Kuznetsov NK-12 turboprop. It's an engine, it's a massive engine which operates until this day, that delivers 12,000 kilowatt of power. Massive. So they built it so big that there was no propeller that would have substitute torque. So they needed to have a contra-rotating prop. So from the 1950s onwards, 14-stage axle compressor, 5-stage turbine, annular combustion chamber, so about 12,000 kilowatt, enormous. Better SFC than the Europrop TP400, they claim, but I mean, these are old engines these days. They powered 7 aircraft, so the Tupolev 95, which flies to this day, the Tupolev 114, the Rossiya, which doesn't fly anymore, and a host of other ones. The Antonov 22, is, you know, Ukraine had one operating until 2 years ago, and apparently Russia has 5 of them flying, but we are not 100% sure whether they're flying or not. And the anti-aerodynamic chronoplan is an airplane that was designed to fly close to the water. Propellers, there is a company still operating in Russia called Aerosila. It's responsible for the production of all their propellers, contra-rotating propellers. These days are designed by Tsagi, which is the central aerodynamic office. So characteristics here, I won't go through those. And here are the drawings of those massive aircraft. You see there how they compare to humankind. So on the left you see the Antonov 22A, beautiful airplane. As I said, the Aerosila AV90 with this 6-meter diameter, 6.2 meter diameters, and the other one slightly smaller props. and this aircraft is still flying. This is the Bear. The Bear. I'm going to show you a picture of that. So both of them are flying. Well, I'm not too sure about the one on the left, but the one on the right is flying. So this one is a video of the aircraft named basically you see 09307, which was destroyed within 1 week of the start of the war in Ukraine at the Antonov factory. And here you see it lands in an African unpaved runway, and it operates in very challenging conditions. And then here is the Tupolev 95 Bear, and this picture was taken at an air show above Moscow before COVID. So that is actually flying. And it's amazing what you find on the internet. So I went to look at one of the air bases, one of the Russian air bases. Well, you can find out which one it is because there are the coordinates in there. And what you see here, you see the Bear, and you see the 160, the Blackjack, which is a different aircraft. This is a supersonic, highly configurable jet. But if you look at the Bear, there are three. There are four. There are three down here and one over there. And if you look carefully, the props are on the floor. So why do you think the props are on the floor? In fact, one of them, at least one of them, has some missing parts of a wing. My guess is that they haven't got the capability to keep this aircraft on the flights for much longer. Okay? What they're doing, they're cannibalizing blades, gearboxes, engine, the turboprop, and they will fly them for as long as they can, but I don't think they will have the capability to keep it going for much longer. Certainly the one at the bottom right is not going to fly, but it's not going to fly at all, but the props are on the floor. You see, there are three props there on the floor. And they're going to be refitted back onto the aircraft. Modern Russian aviation, so we're talking about 1990s, so they designed some advanced prop fans on existing aircraft, and they used them as a test bed. So the Yakovlev 44E it was unveiled in 1991, in fact, at an air show. I think it was the Paris Air Show. A massive aircraft, as they like to do. It's an early airborne warning vehicle, so there is a radar on top and you go up and down. But since then, I think he's not been flying. He's just a prototype. And the Ilyushin 76LL, so the Ilyushin is still flying. He's one of the basically he's a backbone of Russian aviation. And this was an experiment in which they basically replaced one turbofan with a contra-rotating prop. So, and they run some test flights with that. So you see on the inboard side. Noise. I said, since the 1990s, we're already concerned about noise. Now, there was no research done before 1950s. Nobody cared about noise, but nobody knew anything about noise. In fact, Karen and Brett, both these are the chief engineer and the chief aerodynamicist at Hadland, which I was mentioning, near where I live, say there is little that can be done in the design of the propeller itself to minimize the noise problem. If they live to this day, we can do a lot more on the design of the propeller to minimize noise. We can do amazing things. But they're not around. They had to design, on the basis of their engineering knowledge, not on the basis of computational simulation capabilities. Solutions known in 1950s were, reducing the tip Mach number, increasing the propeller fuselage distances, and synchrophasing, basically controlling the rotational speed, the phase of one prop against the other prop. So the earliest acoustic measurements I know are the 1980s, 1988, 1986. All those are actually documented in reports, which are mentioned there. And for anyone who wants to do a bit of research in that area, that's the way to start. The Tupolev 95 is the noisiest ever airplane. I think it could be heard from below the sea surface. I think it could be heard from a submarine. The interesting thing is that it's still flying, and because it's still flying, there must be measurements somewhere. And I'm not able to see those measurements. And now there is a war, certainly they're not going to fly beyond you know, the country borders and the other country which are fighting for. So buoy measurements on UDF usually is unducted fan. Installation effects can include several dBs, so very noisy things. There are some videos on the internet on the Antonov 22, on the Rosia, on the Garnet, but really, we're saying noise cannot be analyzed. You cannot transform the video into a noise level that can be used in a digital way. So the data are not actually used, can be used in the modern simulation, techniques. Okay, research today is about open rotors. There are various embodiments of these open rotors. I won't spend much time on this, otherwise it's going to be until tomorrow. So there are four main architectures. One is the push prop fan. So you see the props are front, the engine is back. On to the right you have the gear, the tractor prop fan. So there is a gearbox in the case. So we are reintroducing the gearbox both left and right. And in the bottom case, when you have direct drive, both pusher and ducted and unducted, there is no gearbox. The gearbox is a problem because all the power goes through the gearbox. That adds complexity, adds weight, adds requirements on lubrication. So gearboxes are always a worry. So either pusher or tractor, direct drive, or is unducted or ducted. These are prototypes. There is a lot of research, a lot of tests on this type of designs which are modern. So just a very quick critical review. So first of all, transition from IC engines to turboprops. So in 1940s, late 1940s, early 1950s, aircraft lasted very little time because there was this new technology called the jet engine, and you just couldn't avoid it. But eventually, the jet engine won, and the IC engine, was left behind. So the science became obsolete very quick. So some notable examples, moving from piston to turboprop, like the Northrop XP35, the Blackburn 54, and others, Western the Wyvern. So they moved from IC engines to turboprops. Some others moved from contra-rotating propellers to single rotating propellers, like Northrop again, the Hughes XF11, which was piloted by Mr. Hughes himself. In fact, in the only flight that he had, he crashed and badly injured himself. It's a well-known story. And he never fully recovered from that crash. He wanted to pilot his own contra-rotating props. And then would be technical failure for the Douglas A2D, the Hughes again. So technical failure because there was a problem with the gearbox, there was a problem with the pitch control, very complex designs. So the difficulties were all the same. Scarcity of time, there were no engineering simulation tools, and more importantly, this is a rule about is valid everywhere in life. It's not only aerospace engineers. It's like the senior guys who tell you, I know best, and we do as I say. And there were senior engineers, which I'm not afraid to name, if I could name them, that they just got it wrong on day one, but they knew best. Until we were proven wrong, until people lost their lives. So the solution of the individual problem doesn't open the route to viability. So if you solve the problem of more propulsive efficiency, doesn't mean they actually have a viable product. You create more problems on the side, so the side effects. So the fuel is not necessarily the highest cost item, especially today. You don't have to worry about the fuel. You have to worry about the airframe integration, the maintenance burden, the availability, the overall risk, the acoustic certification. And people in the 1940s and 50s didn't bother about anything like that in the asterisk. Say, let's build and let's go. So I think the only viable option today is a single rotation propeller, aft-mounted turbofan, like we have in the Dash 8 Q400 and some business jets. That's it. So, to give you some conclusions, so the CRP show potential gains in mission performance, which can only be achieved at the cost of multiple engineering problems. So you solve the one, you create 10 more. In the UK, we had the notable success in military aviation. In the commercial aviation, there was no success, but as I said, there were lots of politically driven projects, and they all failed. In the Russian and Soviet Union, there was success in both fields with NK-12, so they powered several airplanes with a single turboprop. In the modern world, we have prop fans and open rotors. Apparently, they burn less fuel, but they create a little more noise. With the fuel cost drop in the 1990s, the wise men decided there was no worth putting any money into this. The fuel was cheap enough. The problem is, the engineering promise was still there, so they walked out. And that was the end of it. There was a revival in the 1920s, considerable laboratory tests, and the final, most beautiful one is this. Is a Safran open rotor, is on test rig, and by the way, it never flew. It was a test rig on the ground. Because what they said after, there was a project where they got 50 million euro, 50 million euro. They declared the new open rotors are not yet mature to be considered for certification in 2022. So they wanted probably another 50 million euro to proceed with an idea which, in my opinion, has no future. And with this, I think I conclude, and I welcome any question.
Very good.
Yes, sir.
Why did Russia succeed to a certain extent? Why did they just carry on doing it?
Yes, it's because they had, well, I don't have a picture here, because they had this monster engine called NK-12. Okay? So there's an interesting story about that engine. The engine, actually, the ideas of the engine started in the late 1940s. The engine became operational in, I said, 1955. It was so powerful that you need to build an airframe around the engine. And the only way you can absorb that level of power, which was almost 12,000 kilowatt, was to have a contra-rotating propeller. In other words, you got to match the torque you have on the engine to the torque can be absorbed by a propeller. If the engine is too powerful, that's not possible to operate. So a propeller which can absorb 2,000 kilowatt of power at the same point cannot be matched to an engine which delivers 4 times as much.
So it was the necessity of this power of the engine which required...
Yes, they were not going to, they were not politically, they were not going to get rid of the engine. This was the Cold War. They were not going to get rid of that engine, and I think they built aircraft all around that engine. So the main point is the correlation between the power that can be absorbed by the propeller and the power that will be delivered by the turboprop. There must be a match. In which case, they had 4 blades. They could add another 2, but ultimately they decided to contra-rotating props was a better solution. Yes?
So with a traditional jet engine that has a crankcase,
Yes?
it has to be shown during testing that a blade off event
Yes?
is contained within the crankcase.
Yes?
How can an open rotor be allowed that doesn't have anything to protect that blade from anything?
Yeah, okay. Yeah. That's a contentious issue, because you can ask the same question for a single rotating propeller. But somehow single rotating propellers have been able to prove on certification that they would not be under the most critical circumstances that played out. I wouldn't know how you deal with that. They try to do things like, for example, for aft-mounted props. I don't have a picture here, unfortunately. I wanted to keep it short. They try to actually strengthen the airframe at the point which is on the rotor plane, rather. So that adds weight to the airplane. So imagine this contra-rotating props mounted aft of the aircraft, and where you have the props, there is a stronger fuselage, a bigger fuselage thickness, to absorb any blade out, to which the blade actually flies off, toward the inside rather than the outside.
And I'm saying the current project between GE and Safran,
Yes.
FRAeS, that has no future.
You mean this one? I'm not saying there's no future, but I'm skeptical. That's all. I mean, I wouldn't put my money onto that, that's all.
Because of the noise.
It's not only about the noise, I mean, it's also here. Let's go, oops. It's because of the various problems that I said, that the increasing weight, the complexity of the system, you know, the maintenance and everything else. It's not just the noise. This is the problem that, you know, people think about noise. So they come to you, you know, we're dealing with the noise. We come up with this beautiful solution that cuts, I don't know, 1 dB, but it doesn't solve the problem at all. I mean, if I were the chief engineer of one of those designs, I would say noise is just one part of a big puzzle. I need to fit all parts together. Noise, I mean, for certification, they will tell you, we are able to provide, a noise level which is comparable to synchro rotation props. But if you just bought a Boeing 737 or an Airbus A320, you won't, for the next 20, 30 years, you're not gonna do that. Just stop. So just I found the page down there that I was described toward the end. So the presentation is gone now. It's gone blank. So it's all this problem is in here. So you got the maintenance burden. So how often you going to maintain that? Every 100 hours, 1,000 hours, 10,000 hours. The overall risk certification is not a problem to discount, because certification can take 10 years. We've done some analysis on how long it takes to certify an aircraft. It can be 10 years.
Any
Yes.
advantage in using CLPs on drones?
Oh, drones. Yeah, drones. I don't know much about drones. I tend to worry about the real size stuff where they carry people. Drones are easy, because if they don't carry people, you can do a lot more. Yeah, there is a future for them in drones. In fact, talking about contra-rotating props, they are used by at least one designer of this. It's called urban air vehicles. One of the companies I know is a Chinese-owned CEng. So it's 4 contra-rotating props. Again, I'm skeptical, because having contra-rotating props, we have very high downwash, so you can't be anywhere close to the aircraft. So that's one thing. And then there is the issue of single point failure. So if you have 4 props, where one fails, because there is no cross-shaft coupling in this systems here. So each of them relies on the power of an independent electrical engine. So if you lose the power from one, then it will be very, very difficult to balance on the remaining 3 operations. But for the contra-rotating props, with for example, hovering on the ground, they have to maintain bigger distances from the aircraft for ground operations.
Any more questions at all? No.
Okay, so we close here, and I thank you very much. And if anybody comes up with a question at a later time, you can always call me on the email, and the email is on the front page, so I'll be there. And I think, I don't know if it's here, I have a small video to show, so this is my email. You can contact me there, you can find me around. I want to check if I have a video to show here. Yeah, there is a video. Sure. So this is out on the internet. I'll show you. This is the Antonov 22. And then I think
it's in now.
The aircraft I was saying was destroyed 2 years ago at the Antonov factory. A real monster. And some of the research we've done here in Manchester with my colleagues is on dust injection by these engines. So we looked at the effects of dust intake and the intake protection. So this is serious. These operations are very serious. And by the way, the props are not synchronized. You can see that each of them rotates a slightly different RPM. RPM is about 735, plus or minus a few. Interestingly, this aircraft is the APUs are low in the sponsor, so you can see the intake which is in front. So the APU is ingesting a lot of dust.
So, Antonio, on behalf of the branch and everyone here tonight, I'd like to say thank you for a really interesting talk. I think what you've certainly done for me, and I'm sure everyone else here, is sort of shone a light on a part of the aerospace industry over the last 100 years that certainly I didn't know a great deal about. I knew what contra-rotating was, but I certainly did appreciate the history and how that aligned with some developments in the UK aerospace industry as well as the US and America. I particularly appreciate how you framed the start of that conversation. You sort of threw out the idea there about sort of historically efficiency versus the sort of technological, the challenges of technology in terms of this design, and then framed it quite nicely at the end there with your critical solution, your critical review. So thank you for that. Small little things actually I've picked up here. I often wonder why the word airscrew disappeared, but thank you for that. That was just a personal note in history. When you sort of mentioned briefly about the word airscrew and how that got overtaken by propeller from the US, just something that I've often wondered about over the years. Thank you for that. I thought what we did was balance the technology story well against the history side of it. And again, I had no idea about the different kinds of layouts, and I think that was really well presented. Thank you for taking us through that. But for me, I really enjoy the history of the subjects along these lines here, and certainly again, how you showed quite nicely how it aligned with development of the UK aerospace industry, how those big names disappeared, but how some of those aircraft survived, like the Wyvern and the Gannet. And interestingly, how then the Comet, you can clearly quite see, can't you, why interest would wane quite quickly when the Comet comes onto the scene. So thank you for highlighting that. It really tells an interesting story, I think. And then moving on, what else did I pick up while we're going through that? Certainly I'd not appreciated that Russia still had a couple of aircraft still in use. I kind of knew, but I'd not really thought about it. So interesting why they should still be going, or just about, as you showed in that photo. And then thank you for bringing that to a lovely sort of conclusion in terms of the questions that still plague this technology. So whether it's noise, whether it's maintenance, acoustics, all those kind of good things. And I suppose my parting thought on here was, it feels to me like we've got a really interesting technological design and something for engineers to really get their teeth into. But maybe what we still don't have is the need. As a businessman, until you've got that need,
Yeah, exactly.
why would you?
So to pick up on the question on the drones before, those drones are electrical. These ones are driven by IC engines or gas turbine engines. A totally different thing in terms of need to drive the mechanism with the gearbox. Those ones have a gearbox. You pass the stick propellers onto a hub and then you start spinning at any RPM you want. This will fixed RPM. Totally different level of technology.
And like you say, and maybe my thoughts on that as well, maybe a more electric and all-electric aircraft might indeed present a situation where this becomes a solution to something in the future that we're not aware of yet. But who knows? But thank you very much on behalf of us.
Yeah.
Welcome.
This is Chris. You want to tonight? Thanks.
That's all that top, isn't it?
Yeah, so I have to move this.